So we're going to wait a few moments until everybody has a chance to log in. Yeah, so I think we can get started. So it's a great pleasure to introduce José Antonio Carrillo de Aplada for this plenary lecture. He obtained his education in Spain and held positions in Granada at the University of Texas and in Barcelona. He is most known to many of us as a faculty member at Imperial College in London, as chair of the Applied and Numerical Analysis Group, and he recently moved to the University of Oxford. José obtained many recognitions for his work, including a SIAM Prize, the Gam von Mises Prize, and a Royal Society Fellowship, and he is an elected fellow for the European Academy of Sciences and of SIAM. José is known for his seminal contributions to PDE, numerical analysis, kinetic equations, and non-local models and their applications in biology. And these are also interests of myself, so I'm very much looking forward to his talk. So today is basically a day of non-local PDEs. We had a session earlier this morning. We have another session in this afternoon, and now we have the plenary talk. And I find this non-local topic fits really well to this kind of meeting, where we have a non-local meeting. Anyway, so José, I'm looking forward to your talk.
Let me share my screen. Is it all good now?
Yeah, looks good.
Okay, so thank you very much, Thomas, for the nice presentation. First of all, I would like to, in fact, thank the organizers of the conference. It's really very important for many people, for especially the young people that are caught in the middle of this pandemic, in the middle of looking for the next job, to have the opportunity to discuss with others and to exchange ideas during this period. So I think it's overall a very good idea that you went further with the conference, and I hope that there is also a little bit of networking and keeping the time to be able to do the real networking soon in person. Okay, so today I want to discuss about some recent results on nonlinear aggregation-diffusion equations. And mainly I will concentrate on the idea of looking at phase transitions. I will come back to that point later, where we will use mainly these ideas of gradient flows and looking at these equations as gradient flows with respect to certain free energies. Let me start by making a summary of some of the basic notion in this area, because at the end of the day, we are in a SIAM annual meeting, and there will be plenty of people in the audience that may not know too much about the field. And then later, we'll concentrate in illustrating this phenomenon of phase transition in three cases. I will start with the SAN model that comes from alignment in math biology, and then I will go back to more classical problems in Fokker-Planck, nonlinear Fokker-Planck equations. Okay, so let me start by just reminding very basic models in terms of particles. I mean, for me, I'm going to start thinking in terms of a system of M particles which are interacting through forces, and in where I assume that the inertia force is negligible. So then I can write that the change of the position at each time is just given by the sum of forces. This is what it means in this relation over here. So I'm assuming that the particle xj is producing a force onto the particle xi, which is given by the gradient of a given function that I call the potential there. So this form, it looks like it's very particular, but in fact it's very general, and it includes many non-local models that have been proposed both in physics and in math biology. So The idea is that, of course, then there will be some evolution of the particles towards a possible steady state in which you arrive to a kind of a stable configuration. Let me show you here an example, just to tell you that depending on the potential, those configurations might be somehow complicated, and even depending on the number of particles or even at the continuum level, they can be really complicated. So you can write, you can write, that's the end point of the simulation probably at some, and you can write the continuum model associated to that discrete evolution in terms of the evolution of a density of particles or of individuals at time t. So if we call rho of xt that density of particles that you could normalize and then talk about probability densities if you want, then you could say that the velocity field generated by your density is obtained in a similar way to what you do here in terms of the particles. So meaning that the particle located at position y is producing a force at the position x, which is given by the gradient of the potential, and then you sum up all the forces with the right convention with the sign here, that gives you the velocity field. If that's the velocity field felt by the particles, it's normal to expect an evolution of that type for the density of particles. You're going to have a kind of continuity equation, but a kind of nonlinear continuity equation where the velocity field now is given in terms of this convolution with the gradient of the potential. So we can think, if you want, and in most of my talk, it will be the case, that the potential, the non-local part, is in fact going to model the attractive part of the interaction. In the previous slide and in the simulation I showed you, there was an attractive and repulsive potential. So repulsive in the short range, attractive in the long range. But in many cases, in many of these models, you include somehow, you do a separation between attraction and repulsion. Attraction is modeled non-locally, and attraction is modeled attraction is modeled non-locally, and repulsion is modeled even locally. How do you get to that? I mean, you can obtain those models from the previous one in certain by taking certain limits. So, for instance, by assuming a very localized repulsion, that you end up in a kind of nonlinear diffusion term like this one. So, in such a generality, the question here would be. An interesting question is, when does a balance between the attraction and the modeled by the non-local term and the diffusion, which models the repulsion, happen? And if that balance is achieved in certain stable configurations, how do you find these stable configurations from the previous evolution? The basic models that we will see later on, they have in common certain structure. And the common structure, as is already on my title, is that they are gradient flows of certain energies. In fact, those equations I just showed you in my previous slides, they can be written at least formally as gradient flows of this free energy functional, which makes perfect sense in terms of an energy, in the sense that if we think in terms of particle interacting by physical forces, this part is like the potential energy, and this part is like the entropy of the system. And in fact, the notion to understand this as a gradient flow, it needs some advanced notions of gradient flows in metric spaces to understand it in a completely rigorous way. But they can be seen as gradient flows with respect to what is so-called Wasserstein distance. This is something that goes back to works 20 years ago, almost. And in fact, the way to see that is that the equation that I wrote before can be written in this form. It can be written as a continuity equation where the velocity field is exactly given by minus the gradient of the variation of the energy, variation that leaves the mass of rho unchanged. So variations that conserves the fact that the rho has a certain mass or is a probability density we are normalizing. So you do that variation, at least formally, in this kind of function, and what you get as the variation is exactly the potential combined with the rho plus certain nonlinear function of rho that choosing the right relation between this phi and this p that appears in my equation before here in that way, then you get to write the equation in this form. And once you have that form, you realize that somehow easily just one integration by parts, if you can do that and it makes sense, gives you that this is a good Lyapunov functional for the system, in the sense that it decays along trajectories, and in fact it's a strong Lyapunov function in a sense, because unless you are in steady state, that would be strictly negative because of the gradient of the variation. Okay, so that's somehow the basic structure that is behind these models. And then you understand why we are interested then in finding local minimizers of the interaction energy. And not only finding, because we expect them to be locally stable, at least for the dynamics of those equations, which are gradient flows of those energies, and also because in general, critical points of this energy will correspond to possible steady states of those equations. So now I can rewrite better what I meant by the balance between attraction and repulsion. A balance between attraction and repulsion means finding the conditions on W and the nonlinear diffusion in such a way that we have some hopefully non-trivial minimizers or local minimizers. Let me mention that this kind of question has appeared classically in at least these two fields, in crystallization and statistical mechanics, but in those cases the potential is very singular, it's not even locally interval. I'm not talking about those cases, but nevertheless there is also an important question, and then this question has to be rephrased, not in probability densities. In the case of semiconductors or chemotaxis, which is one of the typical applications of these models, then the potential here, either attractive or repulsive, is the Newtonian potential, and both of them are interesting for different reasons. And there are other fields in which, let's say, a bit more modern, they have been these ideas have been introduced, or they have been considering related problems in those fields, like in infield games, fractional diffusions, or in random matrices. But let me showcase here two samples in math biology in which this equation shows up, and this question about phase transition is also interesting. That's where I want to concentrate. One of them is in particle, in particle models or individual-based models in collective behavior. So you probably have heard talks about swarming and applications of these ideas in collective behavior of animals. But they are essentially what you want to explain is the formation of these large coherent structures that you see in nature based on certain basic rules of interaction between individuals. Some of these models, they are based in what is called the zone model, three-zone model, in which you have certain basic mechanisms of interaction between the particles, like the ones that I'm listing here. So let me just talk about one particular model. This particular model includes attraction and repulsion among the particles through this kind of pairwise potential. Here, I'm not neglecting the inertia term, so it's a second order model. So like Newton's like equation. Then there is a term that makes the particles to be going to an asymptotic speed if there were no other effects. It's kind of the self-propulsion term. And finally, there is a term which is now usually referred as the Cucker-Smale term, that is a basic model for alignment. So what it means here is that you are doing a kind of average of the relative velocities between two particles in the system with weights that are depending possibly on the positions of the agents. And typical choices for some of these potentials that make sense biologically, they're biologically reasonable, are here. So In those models, in this particular model, for instance, what you get easily is what is called the flock profile. The flock profile means that what you see in a natural way is that the particles, they arrange depending on the potential in some particular spatial configuration, while they arrive to consensus in their velocity moving in certain direction. So as you can see in this simulation here, that at the end of the particles move in certain direction with certain particular interparticle positions. Of course, this depends a lot on the potential, and the question is the potential will choose probably the shape in space once they arrive to certain equilibria to move in certain direction. Here you have two other examples with other different potentials than the ones that I used in the first slide. So the question is, for instance, how robust are these structures if you have, for instance, noise on them? Okay, that would be a question that we are going to come back in the main part of my talk. As I said, another application that is quite classical is the problem of chemotaxis. And let me be a bit more precise than what I was in the previous comment on this. So if you take the basic chemotaxis model, which was introduced by Keller and Segel at the beginnings of the 70s for the movement of cells by attracted by a certain chemoattractant in a petri dish. That's why it was placed in R2. So essentially this kind of experiment in which somebody with a pipette is putting some chemical substance to which these cells are attracted to, and then they direct their movement towards the source. Okay, you want to do a model for that, not for this kind of number of cells that you have here, or amoeba, but rather for 10 to the 6, say, or 10 to the 8. And then they arrive to some model, basic model like this, in which I'm writing already as a kind of nonlinear diffusion, but the basic model was with linear diffusion, and they have this up the gradient movement of the cells. Here, N represents the density of particles here, and C represents the chemoattractant concentration. So of course, if you here invert the Laplacian and you write C in terms of M by a convolution with the Newtonian potential, and you insert it here, you come back to the model I showed you before. And in fact, that model with nonlinear diffusion is an interesting simple model in which you can test how complicated the number of stationary states and their stability can be. So let me just give you an example to start to get into the main part of my talk. So the sample is nonlinear diffusion, exponent 2, and the chemoattractant, exactly the chemotaxis problem. So here you have the potential, and in fact, I'm going to keep it time dependent. I'm not going to neglect the time dependency of V for this, because it doesn't really matter when we are talking about the steady state. Of course, for the evolution, it will be different. But, and I'm going to consider it, if you want, in a bounded domain with no flux boundary conditions, and here, in fact, is on an interval. So just in one dimension. So here I'm using chi as a parameter that gives you the typical strength ratio between the diffusive part and the attractive part, okay? So as chi gets larger and larger, the attraction is stronger than the diffusion, okay? And it's nonlinear diffusion exponent 2, as I said. So here you have the simulation of two different initial data, one symmetric and one asymmetric, for the same value of chi in between certain values that it doesn't really, it's not really important here. The interesting thing here is that, for instance, in the case of symmetric initial data, you can see that you get, and in fact, we stopped earlier the time that they need, but you get to something which is constant as t goes to infinity. Of course, the constant some constant steady states are solutions of the problem in this case, in the case of the bounded interval. While here, in the case of a symmetric case, what you get is towards one configuration that is compactly supported, and it's all its support is near to the boundary and gives you that certain shape. Okay, so in fact, the situation can be, if you look just at the steady state of that problem, is quite complicated. What you have is you can find them all explicit in this case. You can find many steady states explicitly, and you can realize that you have infinitely many bifurcation points from the constant steady state. The constant steady state, as we said, for every chi is always a solution in an interval. But from certain values that I have here, the values corresponding to the previous case in the interval minus half, then you have this kind of bifurcation points. In fact, before the first bifurcation point for a small chi, the diffusion wins, and at the end, the constant steady state is a global attractor of the system. But then for each of those points, in fact, you have infinitely many stationary states that emanate from the constant. And then if you go along the each of the branches, you get other steady states, which corresponds to half, what we call half bump, one bump solutions, or several bump solutions that we can construct. So in fact, you have infinitely many that you can just compute by hand. So this gives you the idea that the general relation between the nonlinear diffusion and the potential that you put here can be complicated to discern between the cases in which you have or you don't have this kind of bifurcation. Okay, so let me then concentrate now on this phenomenon of phase transition for the rest of my talk. And let me start with what we call the local Cucker-Smale model. Yeah, so this is a model for alignment. So I come back briefly to the model that I just showed you for particles before, for the second order model. If we just keep, now we have noise in the system. We have this term that was fixing the asymptotic speed of the individuals, and I have only alignment. Here there is no attraction or repulsion. That is only alignment. So there is this tendency to go towards the mean velocity. In this case, it's very simple alignment term. Okay. In fact, this would be the PDE that is behind that system of M particles I showed you before, and it's a kind of kinetic model. But let me have a look at first. It's a kinetic model because it's a distribution of particles both in position and velocity. So, but let me look at solutions that only depend on velocity to see what's the typical velocity distribution. So we just look at the velocity distribution, and we just think that F is just homogeneous in a space. That's the kind of PDE that we are interested in. And in fact, this PDE has exactly the structure that we were discussing at the beginning of the talk. In fact, it can be written as a gradient flow with a free energy that has an additional term. It has a given potential, which we call here the confinement, which is the one that leads to the term here of the asymptotic speed. That is a potential that looks like a double well potential here. While the alignment term becomes a second quadratic interaction potential, and the linear diffusion leads you to the term of the entropy at the free energy. So in fact, that's the free energy that we have. That is very similar to what I was showing you at the beginning, just in the case of linear diffusion and this confinement. And now the question is, how many steady states do we have depending on the noise? If the noise is strong enough, we would expect that this destroys the fact that there is an alignment. So it should give you that it's equally probable to go in one direction or another. That's the case in which it is probably more probable that you have something, so you have something which is symmetric in terms of the velocity, in terms of the mean velocity. While if the noise is small, you would expect that the term of alignment gives you some preferred direction of movement. That's what you expect. Is it possible to have that? Okay, in this particular case, there is a simplification with respect to the general case I will discuss later, and it's the fact that your nonlinearity in the equation is one-dimensional. What do I mean by that? That the nonlinearity here, the only nonlinearity comes here, and the UF is the mean velocity of F, but then this is a moment, it's an integral of F. So then it's somehow I mean, I said one-dimensional, but it would be the dimensions of the space in where we are. Okay, but we can always, by symmetry, fix the direction, and then we can think about that as one-dimensional in a sense. So because of that, if you look at two stationary states, you get this relation for stationary states. So the stationary state should satisfy this. And I say it should satisfy this because this is not a full expression, because UF depends on F itself. So I had to find the possible Fs that satisfy this relation. So in other words, I had to find the F such that its mean of this form such that its mean is given by U. So that you can do it by looking at the zeros of this function. And that's why you see that this reduces to kind of the finite dimensions, because you are looking for the U's now such that, depending on the noise, this quantity is 0, where F is given by that formula here. Okay, in this way you can find all the stationary states. So in fact, what we proved is that we can do a kind of bifurcation analysis of the steady states of this equation starting from 0 noise. So what we prove is that there is a phase transition, in the sense that if the noise is small, you have more than one solution. And if the noise, and then you have a solution which is whose mean velocity is not 0, while for large noise, the only solution is the one corresponding to U equals 0. So the mean velocity equals 0, there is no preferred direction, which gives you the corresponding Maxwellian here. How this is done? So in fact, you do just a plot of this function h of ud over here, depending on the noise. Then you can see that for a small noise, it's easy to see that it's going to have an S shape that is going to give you this in one dimension, at least 3 roots, while for large noise, you have something that is decreasing, and then you see that there is only one root, which is the 0 root. And in fact, that's numerically speaking, but in fact, you can show that. And what you can show is that for a small d, we use Laplace method to produce a branch that starts from the Dirac at a certain velocity at 0 noise. So we do some kind of implicit function theorem in finite dimensions, because we prove it for the U, that then implies that you have this branch of solution emanating from a Dirac that gives you this branching from 0 noise. While for large noise, the solution, we prove that this is really strictly decreasing, and then there is only one solution, the 0 solution. So in fact, what we prove is that we have this branch, okay, and that for large noise we have just constant. This is what you get by numerical simulations in any dimension here for certain values of the alpha parameter, which was in front of the fixed speed term. And you see that you have a clear branching, a clear phase transition that occurs at certain values. This has been studied recently in 2 dimensions, and the exact value where this happens. And in 2 dimensions at least, this is fully solved in the sense of finding the right phase transition and the asymptotics. So just to end with this case, what you see is that for large noise, you're going to have something symmetric. As this noise becomes smaller, you get something that gives you a preferred direction. That is in velocity space. Okay, so can we obtain much more general cases in which you have this kind of bifurcation for more general equations of this form? So this is the next thing I want to discuss. And in fact, I'm going to consider this general class of solutions. And I'm going to start to place myself in the easiest possible case, which could be periodic boundary conditions in space. So here now we are working on the torus, and I can get either linear or nonlinear diffusion. Let's assume that it's a power law. And here we have a general potential that could be whatever it is, attractive, repulsive, whatever you want at this point, which I'm going to assume that this is smooth. Okay, let's not, in principle, I don't want to complicate myself on the regularity. We can get some results in which W is not smooth, totally less smooth than C2. But let me just place the difficulty on finding the bifurcation points. Here, kappa again means the interaction ratio between noise and attractive strength. So there is one example which is very classical that enters exactly, fits exactly this setting, which is the case of the noisy Kuramoto model for synchronization of oscillators, in which your potential of interaction is a cosine. And here is well known that there is a critical value of kappa, such that if kappa is small, there is no synchronization of the oscillators. If kappa is larger than this value, there is with the phase locking phenomena. That means that they localize in a certain frequency. Okay, so the goals would be conditions on W such that we have bifurcations, and conditions under which we have phase transitions that I will explain better what do I mean. So in general would be to understand better the energy landscape for this kind of gradient flows. So just to understand some of the statements I'm going to write in the next slides, let's introduce some notation since we are in the periodic setting. So I will consider just Fourier modes, which are defined with these formulas. Here, theta k that will appear, unfortunately, in a cumbersome way in some of my statements, is just the normalization factor on these Fourier modes in d dimensions I'm defining here. And let's start with the concept that plays a crucial role in this, which is for the potentials to be H-stable. This concept was already used in statistical mechanics for crystallization, and it was also used in some classification about the possibility of having, well, about certain qualitative properties of the swarming models by Andrea Bertozzi and collaborators. Here, we rediscovered it some years ago in terms of how to understand the system or non-system of minimizers of the interaction energy, and here appears again in a very natural way. So H stability in the case of periodic setting means that if a potential is H stable, means that it's positive, its Fourier modes are all non-negative. So when we will say that it's not H stable, means that at least there is a negative Fourier mode. Okay, so the free energies associated to these equations, depending on n larger than 1 or n equals to 1, are written here, just to make the difference between the porous medium or like nonlinearity and the linear diffusion case. As I said, they are both gradient flows, as we were saying before. And the first thing that one can say is that if the kappa is small, so if the, let's say the diffusion is strong, or the potential is not, is stable, then the free energies, they have only the constant steady state as the unique minimizers. So nothing complicated may happen in that case in terms of the system of the steady states. So the interesting cases that appear are when the potential is not H stable, or we are getting K large in this. For both cases, what you can write for the steady states is that, in fact, they have to satisfy a kind of self-consistency equation. Now, the self-consistency equation is much more complicated than in the case of the one-dimensional Cucker-Smale kind of nonlinearity, because now the solution has to satisfy that this is constant. That it has to be this is the zeros of this function is what is going to give you the steady states, and the same here for some constants for in the case of the nonlinear diffusion. So I don't want to bother with that. And yeah, the first thing I want to say, at least for linear diffusions, is that this we can have a characterization, or we can characterize the steady states in terms of the zeros of this function before, or this self-consistency equation. and also in terms of being critical points of the free energy. So the three concepts in the setting that we have are equivalent. So in order to find stationary, the bifurcation branches, we are gonna use the self-consistency relation for so the function fk of rho. So we are gonna look for zeros of this function. Okay, so in short, we want to explain, for instance, in the case of the Kuramoto, that's the typical thing that you have and what it was known. For kappa small, you have only the constant steady state. For kappa, at kappa c, you have this branching happening where this becomes unstable and this becomes stable for the dynamics. And this is the cluster solution along this branch here. So let me start by explaining the main result that we have for m equals 1, which is similar, but in a completely different topology in the case of nonlinear diffusion. And let me explain you or walk you through some of the technical things that are written now on the slide. So the important thing is to understand these two conditions. So if W has any negative Fourier mode, which is isolated in this kind of sense, in the sense that there are no, the number of Fourier modes such that this quotient is equals to 1 is only 1, then that produces a bifurcation point in the sense that kappa star, which is related to this value, this negative Fourier mode in that formula, is a bifurcation point from the constant steady state. And from that constant steady state at that value of kappa, you have this curve that branches out. Okay? This is by using Crandall-Rabinowitz theorem and looking at the right conditions to study the structure of the branch. Okay, something very similar happens for m larger than 1, and I don't want to get into the detail of this, but rather just to say that we have essentially the same kind of conditions in order to find the corresponding value of kappa star, which now is different because the free energy, the consistency equation is just simply different. Okay, so these, by the way, these bifurcation results include many cases that were in the literature, and I don't want to go through them. And rather, I would like to concentrate on conditions now that you can classify these bifurcations. So what do I mean by classifying the bifurcations? I mean I'm going to define what it means a transition point, and I'm going to define what it means a continuous or a discontinuous transition point. Essentially, a transition point means that at kappa c, you have a change from being the constant steady state, the unique minimizer of the free energy, to be to find something that is not constant, that is the minimizer of the free energy. And this can happen in two ways. It can happen continuously in the sense that in the topology we're talking about, the minimizers for kappa larger than kappa c converge towards the constant steady state at kappa c, and that's the case we will call continuous, while in the other case we will call it discontinuous. And let me just give you a brief picture of the conditions that we find for either classifying it as a continuous or a discontinuous. I say classification, but I rather should say this is our sufficient conditions to have one or the two. So if you are in a kind of a near resonating dominating mode scenario, in the sense that you have several negative modes, Fourier modes for your potential, and two of them in certain sense that I know writing you on the slide are in some kind of additive sense, these two gives you this one, the largest one, then in that case, we can say that the bifurcation, the transition point is discontinuous. While if you have the dominant mode scenario, when you have a negative mode, which is much larger than the rest of negative modes, then you can show that is a continuous phase transition. And these are the results in the case of linear diffusion. And just to finalize with this, I would like to stress two things that happens for the nonlinear diffusion. In fact, this is the kind of resonating mode scenario that I was telling you, a bit more precise in the case of the nonlinear diffusion. And in the case of the nonlinear diffusion, we are able to say a bit more on transition points in some sense and a bit less in another. What do I mean by a bit more and a bit less? What we can say, for instance, is that if M is in between 2 and 3, the nonlinear diffusion exponent, then only discontinuous transition points can happen. While for M equals 4, we are able to give examples of potentials such that continuous phase transition do happen. But in fact, it seems that there is a persistence with nonlinear diffusion to typically have discontinuous phase transition. And we don't know general conditions apart from these two that will give me continuous phase transitions. The case M equals 4 is very particular. It takes advantage a lot about the fact that you can expand somehow the quadratic power. And let me just finish my presentation by making a summary of some of the things I showed you. I hope to have convinced you that these aggregation-diffusion equations could lead to a very complicated bifurcation diagrams and phase transitions. General conditions for continuous or discontinuous phase transition depending on the interaction potential have been at least identified, but we don't have general characterizations of them. And what it would be very interesting is to have more information on the branching structure in some cases. And let me just mention about the nonlinear diffusion case, which has some particular effects, like the persistence of this discontinuous phase transition and the fact that you have one parameter families of solution and bifurcation points. And particularly, let me just mention in words that for a Keller Segel model, in general, you can show that this picture we saw at the beginning motivation of infinitely many bifurcation points with one parameter families at each of the bifurcation points. This is a general picture that happens for Keller Segel model on about the domain. And with that, I would like just to thank my collaborators and the papers in which this presentation have been based. And thank you very much for your attention.
Yeah, thank you very much for a nice talk, Jose. Very interesting stuff. So please use the chat or the question and answer to ask questions if you have. And maybe while you type your question, I have already one or two. Jose, how about higher order bifurcations? So you can have like coarsening maybe, or splitting of patterns or something like this.
Yeah, I mean, that's exactly what I meant in one of the parts that we don't know that much yet, which is how to get more information about the branching here and the different branches that that appear in the diagram. We don't know if they can branch again themselves. We don't have conditions on that, and still, you know, even for the when you have a discontinuous phase transition, the first discontinuous phase transition, we don't have a clear conditions in which that is either subcritical or supercritical in some cases. That would be already a very nice result. What is very for nonlinear diffusion is very interesting. That's why I put the stress on that you have these infinitely many solutions for some of the parameters. So you have that kind of strange, not supercritical, not subcritical, with many solution at those points with respect to the linear diffusion. But for linear diffusion, it would be interesting to know this. We don't know that much.
Okay. Here's a question by Xianchen Wang. Did you prove that the steady state bifurcated from the one parameter of bifurcation points are locally stable? And how would you prove that?
Well, the things most of the results I show is for bifurcations. Still, we don't have that many results about the stability of many of the statements I did. What the exact answer or state of the art, as far as I know, is the following. As soon as you have the constant steady state, in fact, it wasn't that clear how to show convergence towards that in some of the cases I showed there. One can prove that. If you have bifurcation branches, in fact, you can use the gradient flow structure to get some information, meaning that the gradient flow structure will give you at least that if you have finitely many stationary states, then you could say that your orbits are going to converge towards one of them. And this, for instance, is the case of the local Cucker-Smale model. In the local Cucker-Smale model, I had only two possibilities, essentially. So then using the gradient flow structure, you can say that either you go to one or the other. And depending on the initial energy, is going to decide if you go to one or the other. There are plenty of cases in which we don't know the exact answer to that. For instance, when we have infinitely many stationary states, then it's really an open question how to say even if some of them are locally stable or not, and in which sense. So certainly, that's a very interesting and very open question.
Great. So I see there are no more questions. So Jose, thank you very much again for your talk. It was really, really interesting. We have now 1 hour break, and then the sessions start again at 2 o'clock. Thank you.
Thank you. Bye.